Well, in the last class we have started the design for torsion. So in continuation with that, we have started one problem that which we could not finish it. So let us just start where up to which portion we have arrived. The problem we have started, that is your simply supported beam of 5 meter span. So after few iteration, few trials, we have come to the section that is having that width of the beam, that is 300 millimeter, and overall depth that is 500 millimeter. So I think not 500, 550. Yes, 550. So 300 by 550, that is the overall depth. So the self weight that we have got it as 4.125 kilonewton per meter. Design load with that factor 1.5, 4.125 plus 25, so we are getting 43.6875 kilonewton per meter. That ultimate moment finally due to the simply supported beam, we are getting 136.52 kilonewton meter. The factored torsion, that is 37.5, because 25 times 1.5 that we have got it, and due to torsion, what is the equivalent bending moment that we are getting using the modal provision, we are getting 62.5 kilonewton meter. Okay. And finally, we have got that equivalent bending moment, the sum of that for the applied load plus due to torsion, so we can get 199.02 kilonewton meter. So this is the final moment we are getting it here, bending moment. For that we can find out the area of steel. So we shall get the area of steel taking this 199.02 kilonewton meter. So our next step, that is your area of steel. Mu, let us write down all of them. Mu equal to 199.02 kilonewton meter. B 300 millimeter. FCK 20 Newton per square millimeter. Fy 415 Newton per square millimeter. Overall depth D 550 millimeter. So D we can find out here. Effective depth, that is that we have provided here, 550 minus 25, that is the clear cover, minus we can take it, or 20 also. Let us try with 20. I mean to say that we shall provide 20 millimeter dia bar. We shall provide 20 millimeter dia bar. So we can get it as say 550 minus 25 minus 20 by 2, that is the effective depth, which we are getting it here 515 millimeter. Earlier case we took it as 25 millimeter, that dia bar. But here I am assuming that okay, we may accommodate that one within say your 20 millimeter dia bar, maybe 4 or 5, whatever will come. So we can find out, we know mu, b, fck, fy, d, all of them we know. Let us find out that d computed effective depth, that one should be equal to mu by 0.138 fck b, so that we can get it here, root over 199.02 into 10 to the power 6 divided by 0.138 into 20 into 300. 300, that is your width. So we shall get it 199.02 10 to the power 6 divided by 0.138 divided by 20 divided by 300, square root of that, which is coming as 490, say 490.26 equal to say just simply 490 millimeter. What I am trying to say here, that we have provided 515 millimeter. Obviously it is greater than d computed, which is greater than say 490 millimeter, that is required. What we can do, one way we can do it here, that we can take it say 490 plus say 25 plus say 10. So that means we can make it say 525 also we could provide, 525, at least at this stage we could provide say 525. That means if we do it now, again we have to again recalculate whole thing. Anyway, let us do not make that exercise now, but if we could do that one, then we could provide the balanced reinforcement. That means if your the depth within say 2 or within say plus minus say 5 millimeter, say plus say 5 millimeter, say whatever that effective depth required and whatever effective depth you have provided, if it is just simply say within say 5 millimeter, then what we can say, almost we can say that is a balanced section. And if it is a balanced section, then what we can do, immediately we can provide, immediately we can do, that means z we can calculate, that z equal to d times 1 minus 0.416 x by d. So what we can do immediately, we need not calculate that you say from that equation, quadratic equation. What we can do, x by d, that is your say 0.48 for the balance section. So z will be equal to 1 minus 0.416 times 0.48. So we can get it 0.9968, and which comes as 0.80032 d. That means simply 0.8 d. That means if we could provide the section within very close to the balanced section, then immediately what we can do, the z we need not calculate using that equation. What we can do, we can simply take it that 0.8 d, and then we can do our calculation for the area of steel to be provided. But here it is significantly higher, 515 and 490. So what we have to do, we have to calculate that x by d. In few books you will find out that they are using simply 0.8. So there, in that case, what they have done, they have provided that effective depth almost very close to the one required, and that's why they are immediately they are using as 0.8 d, the z equal to 0.8 d. But in our case, we have to calculate that x by d. So x by d equal to 1.2 minus root over 1.44 minus 6.6 mu by fck b d square. What about, let us calculate this one separately. 6.6 times 199.02 into 10 to the power 6 divided by 20 times 300 times 515 whole square, which comes as 0.8254. So x by d equal to 1.2 minus root over 1.44 minus 0.8254 equal to 1.2 minus 0.7839 equals 0.4161. So x by d we have computed as 0.4161. So what about the lever arm then? The lever arm, is it okay? Shall I, okay. So lever arm Z equal to d 1 minus 0.416 x by d equal to 515 1 minus 0.416 times 0.4161 equal to 515 times 0.8269 equal to 425.85 millimeter. In no case that you would, if I consider that, if you remember that working stress method, there we use some parameters, say JD. D is the effective depth and J is the one you would say that from the lever arm, from there we are talking. Another one is K. So K and another one J. So here you will find out that J could be, say, minimum, that is 0.8 for balance section, because it cannot go beyond that. And now 0.8. So that means here 0.82, 0.85, 0.9, 0.92, something like that. In that case, it comes that values. So this is the one, that parameter, the J. So J times D in the limit state method you can find out. So which is nothing but, this parameter is nothing but, that is your J in other way. So I have got this lever arm Z. So what about the area of steel? Equal to mu by 0.87 Fy times Z, which comes as 199.02 into 10 to the power 6 divided by 0.87415 times 425.85 equals 1294.4. Let us say simply 1294 square millimeter. So this is your area of steel that you have to provide. So 1294, that is your area of steel. Let us write down here 1294 square millimeter. 20 torr bar, for that AST bar, that for single bar, that is your, say, 314 square millimeter. For 16 torr, AST bar equal to, say, 201 square millimeter. So what we can do, generally we do it, either we use, say, single bar, that means, say, one type of bar diameter, or maximum 2, 3 or 4, all those things we generally do not provide. That means here, if we provide, say, 20 torr, so 314, so 1294 by 314, so that means it is coming 4.12, the number. If we provide that, say, 1294 divided by 201, which is coming as 6.43, the number of bars. And other one we can take it, so that means here you have to provide here, so 314 into 5, 1570. That if I, that means 5 numbers. One is possible, say 5, 20 torr, that is possible. This one we have to provide say 7, which is coming as 1407 square millimeter if we provide say 7 16 torr. Alternatively, what we can do, we shall provide, let us say 3 into 314, that means 3 numbers of 20 torr plus 2 numbers of 16 torr, which comes as 1344. 1344. That means which is coming closer to this one and less than the say for least of these 3. So we can provide 320 torr and 216 torr. Okay. So we shall provide like this. How shall we provide? That we shall provide 120 here, another middle here, another here, and in between we shall provide the 16 then, because we are having 5. So these 3 will be 20 and these 2 will be 16. What about the percentage of steel? Let us calculate, because we need this one to calculate that, to find out that say your critical stress, the shear stress. So let us calculate here percentage of steel. That is equal to 1344 into 100 divided by 300, that is the width of the beam, times 515, which is coming as 0.869 percentage. Okay. So the percent of steel we are providing, that is 0.869 percentage. What is the limit? That also we should check. That is your say 0.85 by FOI. That is the limit, that percentage of steel that you have to provide. That is almost you can say 0.205% or something like that. In that case it will come. But anyway, it is higher than that value. So limiting value always you have to check that whether you are getting that less than or not, that you have to always check. Okay. Now let us come to the other one here. That means here we are providing that 3 numbers of 20 torr and 2 numbers of 16 torr we are providing. Now we generally check it that equivalent bending moment due to torsion, that we have got it how much? So this is overall depth by width divided by 1.7 as per the codal provision, 62.5, and bending moment due to the applied load, that is your MU, that is 136.52 kilonewton meter. Generally that our code says if this value is greater than this one, then you have to provide the reinforcement, top reinforcement of that one, say your difference of that. But few designers they prefer, okay, that we provide this one according to this value. That also, that few designers that they do it. So what we can do, we can at least we can try that value. Let us see that how much it is coming. So in this case, let us take that one independently. For the singly reinforced section, we can again consider independently. But in actual practice, that strictly speaking, what you have to do, already you have the reinforcement as if that one already say balanced. So whatever you are adding, so that one you are giving due to this moment. So we can find out that x by d, which equal to again 1.2 minus the same formula, so equals 1.2 minus root over 1.44 6.6 times 62.5 into 10 to the power 6 divided by 20 times 300 times, let us take that 515. We may reduce that one because that effective depth may be increased, because not necessarily that we have to provide 20 millimeter dia bar at the top, maybe 60 millimeter also may be possible. We do not know right now. Anyway, we can use the same value here, 515, okay, and which comes as 22138 equals 1.2 minus 1.0898 equals 0.1102. So this is the value we are getting here, x by d. So we are getting this one due to this mu means here, please note this mu means due to torsion, not this one. Okay, this mu due to applied load, which is acting, say if you consider that one, that is acting say below, but whereas that our code says that we need not provide, but since some few designers they paper, so let us take that one, let us see that one, because after all we are providing the top reinforcement as a hanging bars. So let us provide that one on the basis of this, that we can always provide. So due to torsion we are getting that mu, which is coming as 62.5 into 10 to the power 6. So area of steel equal to 62.5 into 10 to the power 6 divided by 0.87 FOI, that 415, and that lever arm, which is equal to 1 minus 0.11202 into 0.416, sorry, I think we should write down the other way, 0.416 x by d times 515, and it comes as 352.55 square millimeter. So if we provide the say 20 torr, 2 numbers 20 torr, that will be 2 numbers 20 torr, that means 2 into 314, 628, but 2 numbers 16 torr, because at least you have to provide, always you have to provide 2 numbers, so 2 into 201, so which is coming as 402, closer to this value 352. So let us provide 2 numbers 16 torr. So in the bottom we have provided 3 number 20 torr and 2 number 16 torr, and at the top we are providing 2 number 16 torr. Generally we provide say 2 number 12 torr, say for hanging bars. So instead of that we are deciding on the basis of this value. Alternatively, what you have to do, if this value greater than this one, then we have to make the difference on the basis of that we have to calculate, which is as per code. But in this case we need not provide, but after all we have to provide that top reinforcement, so we can provide in this manner. So what about now the stirrups? So design for SIA, that we have to provide this web reinforcement. So we have got that W equal to 43.6875 kilonewton per meter. Am I correct? That value, let us go back and let me show you, because whatever we have calculated, I think it is here. So that this value, because after taking the 300 by 550 we have got 43.6875 kilonewton per meter, that is the one. So that one we shall take it here as the for calculation of the shear force. So VE, or say here simply say, or VU, say let us say, that is 43.6875 into 5 by 2, which is coming as 46.1875 kilonewton. I hope so. 43.6875 2.5. So I have done a mistake possibly, just a minute. So the value is coming here 43.6875 into 5 by 2, sorry, it should be 109. So 109.218 kilonewton, and TU equal to the same one after multiplication of 1.5, that is 37.5 kilonewton meter, and equivalent shear force, that one will be VE equal to 109.218 plus 37.5 by 0.3 times 1.6. That is the one that as per the codal provision that you will get it, and which is coming as 37.5.3 into 1.6, so 109.218 plus 200, 37.5 by 0.3 into 1.6, 200. So this one comes at 309.218 kilonewton. So equivalent shear we are getting it here 309.218 kilonewton. So we have to calculate, first thing we have to calculate that what is the shear stress, average shear stress, we shall get it. So tau EV equal to 309.218, that is the VE that which we have computed, divided by B is 300 times D, which is here 515. So we shall get it into 10 to the power 3 in Newton per square millimeter. So 309.218 divided by 300 by 515, which comes as 2. Tau C max, that is 2.8 for M20. So less than 2.8, that means we can take this section. If it is more than that, then we have to change the section, we have to change the depth, we have to change. But here 2 Newton per square millimeter, which is less than 2.8 Newton per square millimeter, that is the maximum permissible shear stress. Okay. Now as per the code, that 100 AST by BD, so we are getting here for 0.75, that is in say table 19, and tau C, that is 0.56, and for 1 it is 0.62. For P equal to 0.869 percentage, that which we have computed, P the percent of steel we have already computed, that is coming 0.869 percentage, that is the longitudinal steel we have provided. So for that we are getting P 0.869 percentage. So tau C, that is permissible, 0.56 plus 0.62 minus 0.56 divided by 0.25 times, just let us make that one, 0.869 minus 0.75 comes as 0.5885 Newton per square millimeter. So tau C, that is permitted, that is 0.885, critical, that is 0.5885 Newton per square millimeter. And what about tau EV due to that equivalent one? Yes, we have already come. So that is 2 Newton per square millimeter and 0.5885 Newton per square millimeter. Our code says that minimum steel to be provided. Let us check the minimum steel. Let us say ASV minimum, that wave reinforcement, equal to tau EV minus tau C times B times SV divided by 0.87 Fy. SB is the spacing. What we can do it here, so tau EV we have got it, say 2, tau C 0.5885, B is 300, spacing let us take 200. If it is say 200, we are telling that we shall provide that 200 spacing, 200 millimeter spacing. And then on the basis of that we can find out that area of steel divided by 0.87 times 415. So we shall get it as into 200 divided by 0.87 divided by 415. So we are getting here 234. That is the minimum that we have to provide. We can check what is the required as per the loading. This one required actually that we need it. Now let us find out from the TU and your VU how much we need. The area of shear reinforcement ASV equal to TU by SB. TU is the torsion, B1 D1, B1, so please note B1, this is B1, center to center distance between two longitudinal bars in the breadth direction. This is B1 and this is your D1 in the depth direction. So B1 D1 Fy plus shear force VU due to applied load is V times 2.5 D1 Fy. B1 will be equal to 300 millimeter is the breadth, minus 25 clear cover from one side, minus 25 the clear cover in the other side, minus 20 by 2, minus 20 by 2. Okay, and that one we are getting it as 230 millimeter. What about D1? D1 will be equal to overall depth 550 millimeter, minus 25, minus 20 by 2, one side. What about the other side? Other side it will be, since already you have provided 16 millimeter dia bar, so now we can say 25 minus 16 by 2. Okay, so we shall get it here 500 minus 10 minus 8, so 482. So ASV equal to 37.5 into 10 to the power 6 into, let us say we have already selected 200 millimeter spacing, divided by 230 times 482 times 415 plus VU, that is 46.19 into 10 to the power 3. I think VU, that is different, right? Sorry, I have done a mistake. Yes, 109. 109.218 into 10 to the power 3. Okay. So into 200 divided by 2.5 times 482 times 415. So let us do one by one then. So 37.5 10 to the power 6 into 200 divided by 230 divided by 482 divided by 415, which comes as 163.01 say, plus 109.218 10 to the power 3 into 200 divided by 2.5 divided by 482 divided by 415, which comes as 43.68. So this one equals 163.01 plus 43.68, 206.69 square millimeter. We require 234. We require 234, that is the minimum. Here it is governed by the minimum one. And so 206.69. What we can do it, so let us find out, say 10 torr. So 10 torr we are getting it here 78.5. 12 torr 113. 16, next one is little higher, 16 torr 201, and we have to provide for 234. So 234. Now what we can do, it is coming 200 ASB 234. That means if it is two-legged, it is two-legged because both sides. So one side it will be 117, and it's really a very, very tricky situation because 78.5. I don't want to provide, say here 78. So 234 by 78, say, so 3-legged, that is generally very, very, I do not prefer. Okay. So what I can do, 113 it is coming less, 226, 201 it is quite high, 402. What I can do, what alternative I have to recalculate. Whether I could make it SB, say 190. Let us make it, say, SB 190, and if we can make it, say 226. I prefer 12 torr, two-legged. Let us check it at the rate of 190. Okay, so that I can get it, say, at 226. So ASB, whether I can get it at 226. So let us find out that one. So I can get it as ASB minimum. Let us check it once more. So which is coming as tau EV minus tau C times B times SB divided by 0.87 FY. Let us check it. 2, so minus 0.5885 times 300 times 190 divided by 0.87 times 415. So 2 minus, we need not check it this way, we can check it directly by the dividing also. So which is coming as 222.8. So that means we can provide that 12 torr two-legged at the rate of 199 millimeter. So ASP provided, that is equal to 226. and here we require that 222.8. So these are the, what I mean to say, that this way we generally change it. The thing is that not necessarily that blindly you should do it. We should take, okay, in this case, just if we can make it say 10 millimeter spacing, then reduce it, that immediately it is coming very closer. Why shall we go say 16 millimeter dia bar, and making 16 millimeter dia, say your stirrup, and that is quite heavy. We do use it, but most of the cases we try to restrict it within say 12 millimeter maximum. So 8 millimeter, that is very, very common practice, then 10 millimeter and then 12 millimeter. If you really need it, because you have to make that link of say 16 millimeter, and it is quite heavy, that one, to make it. So that is why we generally avoid that bar. Okay. So let us summarize the thing. So D, that we have provided 550 millimeter, B 300 millimeter, M20, FE 415, then bottom reinforcement, three 20 torr and 2 16 torr. Okay, and here what we shall do it, it is preferable that, okay, just make it that one, yes. So we are providing here, so area of steel provided that is here 1344 square millimeter, P 0.869%. So that just we can check it whether we are fulfilling all the codal provision, the limiting values, all those things. We can stop it here, but it is preferable that we should provide that value also what you are providing. Top reinforcement, that is 216 torr, and area of steel that is provided that is your say 402. Now stirrup SIA reinforcement, (12 torr) 2-legged at the rate of 119 millimeter center to center. So we are getting that summary of design. This is all the information whatever we need. We should mention here of course the clear cover. Generally we make this in the design note, that means when you are doing that you are say drawing, full drawing. So in the right hand side we generally provide all the information, which grade of steel, which grade of concrete, all those things we provide, and then we do the calculation, other things we do it. What we generally do, say for example, just to tell you, I think I should, the common practice in the your say design office, I think whether you can get it or not, let us see. Generally it happens that you say something, could you find out that you say there are some graph type of thing we have written, that lines actually. Generally what happens is that we should have some kind of say that department, so company's name, and then title, then page number, and then who has designed that one, that actually we should have that signature, all those things. This is the way actually we make it for your say for design calculation, other things, and that you, if it is required, you have to submit it also. Okay. So I think this is all regarding say design of design for torsion. Now I think I have not told regarding the reinforcement. regarding the, because we have some time, so I think now I can tell you regarding the reinforcement detailing of your staircases, that which we have not completed. We have done the calculation, but which we have not completed. So let us do that part, that how it comes, where you have to provide the reinforcement, how to provide, let us do that one. What we do it, so reinforcement, so this is your beam, and this is the landing, say it is starting like this, and these are the steps. The steps can be made of bricks, or steps can be made of, say, concrete also. Let us say it is like this. We are getting some kind of thing like this. So we have to provide the reinforcement. We are using, say, WL square by 10, that formula we have got the reinforcement, all those things, and the top reinforcement and the bottom reinforcement. So this is your reinforcement what we need. Please note the detailing. It's not like that we are just simply making here and then we are moving. That is going up. The reinforcement which we are providing here, please note that reinforcement we are providing here, this is in the bottom portion where the tension will be developed due to this type of, say, staircase. It will bend like this. So, we have to provide reinforcement at the bottom surface. What we are doing, we are not doing like this. So, that means if a section like this, we do not provide the reinforcement in this way, neither this way. Not so simple. What we do, we just simply go up and provide the reinforcement, and the bottom reinforcement also, it will go further and come here. So, this reinforcement here, this is one, this is another one, so that there will be no, because if we have only one, there is a chance of that cracking, the concrete will come out. To avoid that one, in this type of junction, we provide the reinforcement in this fashion. Similarly, here also we provide the reinforcement like this, and the distribution steel obviously you have to provide. In all the cases, we provide the distribution steel. So, here as well as here. So, like that we provide the reinforcement, and the other reinforcement we also provide for the top one. We provide the reinforcement here we go like this and we provide that. Here there is no problem because this concrete will not go out, but here there is a chance of that concrete because of the bending. Here that concrete can come out, but here there is no problem, so we can simply use the same directly. What about this length? How far we shall go? This length will be from here we shall start and it will go up to LD, So this is your that LD, the development length, that we have to go up to this, that extension of this one. And these are called distribution steel, this is called your main steel, and these are called distribution steel. So distribution steel will be according to that 0.12% of that for slab. For slab that is 0.12%. Here I would like to say that for slab that is 0.12% for the torch steel. For beam it is 0.85 by FY. Okay. Now where you are not providing any stirrup or shear reinforcement, we can treat it as a slab. So that means there we shall provide say 0.12%. But where we are providing that your say stirrups, there it is preferable that you should provide the reinforcement say your according to beam, minimum reinforcement of the beam. So because the code is silent in this case, what should be the case? Code is telling that you go as per say beam theory, but specifically it does not mention in few cases. In few cases it does not mention that what should be the specific say minimum reinforcement. So you may find that different that company or different say designer using say different kind of say your reinforcement, sometimes say 0.12%, sometimes maybe say your according to the minimum beam reinforcement, whatever it is. So I personally feel that where you are providing that reinforcement for the slab reinforcement only, that means there is no shear reinforcement, we can take it as a say slab. Where you are providing that you say stirrup or shear reinforcement, then we can consider it as a beam. So accordingly we shall take our limiting values for reinforcement. Okay. And only thing you please note that it should not be like this. You should always avoid the this type of say your detailing. In that case what you have to do, the detailing should be, you will go up and then change the direction. Similarly here also you do it, so that in no circumstances the concrete will come out. Okay. I think we shall stop it here. Thank you.